Welcome back to Deep Dive, everyone. Today, well, we're kicking off something I think is really important for anyone trying to master welding inspection. It's the start of our special CSWIP 3.1 exam prep series. Yeah, designed to really sharpen your knowledge, give you that edge, whether you're actually prepping for the exam or, honestly, just want to think like a top inspector. So, our mission today, tackle some tricky multiple choice questions, the kind you often see on that CSWIP 3.1 exam. And we're not just finding answers. We want you to really get the why behind them. So you're not just informed, but truly prepared for what you'll see out there.
That's exactly it. Yeah, for anyone prepping for CSWIP 3.1, look, it isn't just about memorizing facts. It's really about developing that critical eye. That solid understanding that makes a welding inspector truly effective. So we'll break down some key ideas, maybe look at some subtle points that often, trip people up, give you a clearer picture of what's needed, not just for the exam, but, well, for the job itself. We'll dig into not just what the answer is, but the why, the metallurgy, the structural stuff, because that's the knowledge that really sticks, right?
Okay. Let's dive in then. Let's unpack this first scenario, see if we can sharpen that intuition. Imagine you're out on the shop floor. You're visually inspecting the face of a finished weld. Which one of these flaws would you consider the most serious? Is it A, excess weld metal height, B, start porosity, C, spatter, or D, arc strikes?
Okay, this is a great starting point because, well, all of these are flaws. They're imperfections we don't want, but their impact, their effect on the weld's integrity and how long it'll last in service, that varies hugely. The correct answer here, and yeah, arguably the most serious, is D, arc strikes.
Arc strikes. Spatter. Interesting, because spatter looks messy. Excess metal seems like poor technique.
Exactly. You might think those are worse visually, but arc strikes, they're like these hidden assassins. Why? Because an arc strike, even a really tiny one you might barely notice, it causes localized hardening right there in the parent material next to the weld.
Hardening from just a quick flash.
Yeah, that sudden, intense heat followed by rapid cooling creates a very brittle zone right on the surface. And worse, arc strikes often leave behind tiny craters or sharp little notches. So now you've got this hardened, notched area, and that acts as a really severe stress raiser.
Okay, stress raiser, meaning it concentrates the stress at that point.
Precisely. So under normal loads, especially dynamic loads, like think of a bridge vibrating or maybe an offshore platform getting hit by waves, the stress at that tiny little arc strike point can magnify like crazy, and that's often where a crack starts.
So it's an initiation point.
Exactly. And once a crack starts, well, it can propagate, travel through the material, and potentially compromise the whole structure, lead to failure.
So it's counterintuitive. A big bulge of excess metal might look worse, but that tiny, almost invisible arc strike mark could actually be far more dangerous because of the metallurgy, the change to the metal itself.
You've got it. That's why understanding the why is so critical. Compared to arc strikes, sure, excess weld metal height isn't great. It shows poor control, maybe creates some stress if the transition's bad, but generally it doesn't cause that same kind of metallurgical embrittlement, start porosity, small voids. Unless it's really bad or clustered, usually less critical than a sharp hardened notch. And spatter, mostly cosmetic, right? Unless it's hiding something else. So while they're all flaws we need to note and often address, that unique combo of hardening and stress concentration makes arc strikes particularly nasty.
Looking for those silent assassins then. Okay, that makes a lot of sense. Speaking of things that cause problems, let's talk about undercut, another common one. What's the main cause here? Is it A, excessive amps, B, excessive OCV, excessive travel speed, or D, current too low?
Right, undercut. Every inspector sees this. And understanding the root cause is absolutely fundamental. Here, the main driver is A, excessive amps.
Too much current.
Yep. When the welding current, the amperage, is cranked up too high, that arc gets incredibly hot, very powerful. It's like it's digging too aggressively into the base metal right beside the weld toe. It literally melts away some of that parent material.
Okay.
Then as the weld pool cools and solidifies, it doesn't quite fill back in that little groove it just melted out. And that leaves you with a notch or a channel along the edge of the weld. That's your undercut. And the problem is it effectively makes the base material thinner right there at the joint.
Which weakens it.
Exactly. Reduces the cross-sectional area, weakens the joint, makes it more susceptible to stress, potential failure. Plus, like the arc strike, it creates another stress concentration point, though maybe without the same intense localized hardening, usually.
So it's that balancing act with the current again.
Yeah.
Too hot, you're literally carving away the base metal. Too cold, and I guess you risk things like lack of fusion, right?
Precisely. Too cold, you don't get proper fusion. Too hot, you get undercut. And yeah, welders, even experienced ones, can push it too high sometimes, maybe trying to get deeper penetration quickly or just running the machine settings hotter than needed. Sometimes it's technique too bad arc length, wrong angle, that makes the effect of high amps even worse.
What about the other options?
Yeah.
Travel speed.
Well, excessive travel speed can contribute, sure. If you move too fast, the molten metal doesn't have time to properly fill the groove the arc creates, so you might get a shallower undercut. But it's usually secondary to the heat input from excessive amps being the primary cause of significant undercut. Current too low. That usually leads to the opposite problem: poor penetration, lack of fusion. And OCV, open circuit voltage, that's the voltage just before you strike the arc. It helps start it, but it's not the direct cause of undercut during welding. So yeah, excessive amps is the main culprit here.
Got it. Control that current. Now, sticking with undercut, let's say we find some, a small amount, in a fillet weld. Which characteristic of that undercut would be the most likely reason for outright rejection according to most fabrication standards? Is it the A, depth, B, length, C, width?
Or D, sharpness.
This is a really good one. It tests your understanding of defect severity, not just detection, especially for fillets. And the answer, the critical factor, is D, sharpness.
Sharpness, not depth or length.
Well, standards will almost always give limits for depth and length. Undercut shall not exceed 0.5 millimeter depth, or continuous undercut limited to 25 millimeters, things like that. But a sharp undercut, that's often cause for rejection pretty much universally, even if it's technically within the size limits for depth or length.
Why? Why is sharpness so critical? Because, again, it comes back to stress concentration. A sharp notch, no matter how small overall, is an incredibly powerful stress concentrator. Think about scoring glass before breaking it. A tiny, sharp scratch is all you need, right? It's far more effective than a wider, shallower scrape. It's the same principle here. The sharper that undercut groove is at its root, the more dramatically the stress magnifies right at that point. And that massively increases the risk of fatigue cracking, especially under cyclic loads or even brittle fracture. A smoother, more rounded undercut, even if it's a bit deeper or longer, but still within limits, generally less problematic structurally. Because the stress is distributed more gradually, it doesn't have that single super sharp point for stress to build up.
Wow. So, as an inspector, you're training your eye not just for the size, but for the geometry of the defect at a micro level almost, looking for that sharpness.
That's exactly it. It reframes how you assess it. It's not just about how big it looks, but about the shape of the root of that defect. You're like a structural detective, hunting for those tiny features that could initiate a failure.
Structural detective. I like that. Okay, shifting gears slightly, away from specific defects, let's nail down some terminology. A code of practice. What exactly is that? Is it A, a standard for workmanship quality only; B, a set of rules for manufacturing a specific product; C, a specification just for the finished product; or D, a code just for qualifying welding procedures and welders?
Understanding this is really key to knowing the framework we operate in. The best description here is B, a set of rules for manufacturing a specific product. It's much broader than just workmanship standards or a final product spec, although it certainly includes elements of both. A code of practice really lays out the detailed guidelines, the requirements for the entire manufacturing process.
The whole thing, from start to finish.
Pretty much. From initial design things, material selection, all the way through to the welding procedures you need to use. The qualifications needed for those procedures and for the welders doing the work. The inspection methods you have to employ. And finally, the acceptance or rejection criteria for any flaws you find. It covers the whole life cycle.
So it's like the master playbook or the comprehensive operations manual for making a specific thing safely and consistently.
That's a great way to put it, a master playbook, especially in critical industries, right? Pressure vessels, bridges, pipelines. You need that consistency and safety assurance. So while it will definitely reference workmanship standards and point to separate codes for qualifying welders and procedures, its overall scope is much wider. It defines the entire methodology, gives everyone, designers, welders, inspectors, clients, a common language and benchmark.
Right, keeps everyone on the same page. That clarifies things a lot. Okay, final question for today. Let's talk strength, because ultimately that's what a good weld provides. Which of these fillet welds would be the strongest? Assume they're all made from the same material using the same WPS. Is it A, 8 millimeter throat of a miter fillet; B, 7 millimeter leg plus 2 millimeter excess weld metal; C, a miter fillet with a 10 millimeter leg; or D, a concave fillet with an 11 millimeter leg?
Okay, this gets right to the heart of fillet weld strength, absolutely vital concept for an inspector. The strongest option here, unequivocally, is a 8 millimeter throat of a miter fillet.
8 millimeter throat. Why is that the key? not leg length.
Because when we talk about the load-carrying capacity, the strength of a fillet weld, the most critical dimension is its actual throat thickness. Forget how big the legs look or how much metal seems to be piled on. The throat is the shortest distance from the root of the weld to its face, or, more precisely, to a line drawn between the two toes. That's the dimension that carries the load, that experiences the highest stress. So if you're explicitly told you have an 8mm throat, that guarantees the most load-bearing material in that critical area compared to the other options.
Okay, that's clear. So walk us through why the others, which maybe sound strong, aren't quite as good as the 8mm throat.
Sure. Let's look at option C. A miter fillet with a 10mm leg. Sounds pretty big, right? 10mm leg. But for a standard miter fillet, the theoretical throat is calculated as about 0.707 times the leg length. So 10mm leg times 0.707, that gives you a throat of roughly 7.07 millimeters, which is definitely less than 8mm.
Less than 8, okay.
Now, option B, 7mm leg plus 2mm of excess weld metal. Okay, you've added volume, but that excess metal, that reinforcement, it doesn't always translate directly into a stronger effective throat. In fact, if the transition isn't smooth, that excess metal can sometimes even introduce stress points. It's not a guaranteed 8mm throat, not even close necessarily.
So more metal doesn't automatically mean more effective strength in the right place?
Exactly. And finally, option D, a concave fillet with an 11mm leg. Now, concave fillets can look nice, and they can be good for fatigue life because of the smooth transition. But for any given leg length, that concave profile inherently reduces the effective throat thickness compared to a standard miter weld. So even with an 11mm leg, the actual throat will be less than what a miter profile would give, and almost certainly less than our guaranteed 8mm throat in option A. So it really drives home. For strength, always look at the throat thickness first.
That's a fantastic summary. Throat thickness is king for fillet weld strength. Wow, what an incredibly insightful deep dive today. We've hit some really key concepts for anyone prepping for CSWIP 3.1 or just wanting to sharpen their inspection skills. From understanding the hidden danger of arc strikes to why sharpness beats size and undercut and why throat thickness rules for fillet strength. We covered a lot. And the goal, like you said, wasn't just getting the answers right.
No, it was about understanding the why. Getting those foundational principles.
Exactly, because that's what makes you effective, not just in an exam, but out there, making real calls on real welds.
Absolutely. That understanding means you're not just ticking boxes. You're equipped to think critically. Like we did today, going beyond just seeing a flaw to understanding its real implications. That's the most valuable tool you have as an inspector.
Couldn't agree more. So as you all continue your preparation, maybe studying these points further, here's something to think about. How could it really digging deeper into the physics, the metallurgy behind these standards, how could that elevate your skills even further? Moving beyond just inspecting for failures to maybe anticipating them or even helping to prevent them in the first place, becoming a truly proactive guardian of structural integrity, something to ponder, keep digging, keep learning, keep asking why. We'll catch you on the next deep dive.